Okay, team, here we go. Calc Day 1 remotely. So we're going to be looking at 5.3 today. So we're going to start with a couple things that we've done so far in Chapter 5. So theorem so far in Chapter 5, we've got the extreme value theorem. So that was the one that said if f is continuous on a closed interval, a to b, then f has both a max and a min on that interval. So it could look something like, here's my chunk of graph from A to B, right? And so it has a minimum and a maximum. It could look something more like this too, right? Where it would have a minimum and a maximum as well. We talked about local extreme values. So if a function f has a local max value or a local min value at an interior point of its domain, and if the derivative exists at that point, then the derivative has to be equal to 0. Because we know that that would be something like this, and then there's that horizontal derivative where that slope is equal to 0. Then we talk about the mean value theorem. So if f at x is defined and continuous on an interval ab, and it's differentiable on that interval, then there's at least one number c in the interval that a is less than c, which is less than b, so c is between a and b, that the derivative at that point has to equal the slope of the secant. So this was our last lesson, okay? Then we move into new stuff. So we talked a little bit about this, but we didn't actually talk about the theorem. So a new theorem is the first derivative test. So at a critical point C, if the sign on the derivative changes from positive to negative, then that point is a local maximum, right? So if we have a slope that's positive and then goes to a slope that's negative, then we know that that function must be doing something like that, right? If the sign on the derivative changes from negative to positive, so the slope like that to slope like that, then we know that it must be a minimum. If the sign of the derivative does not change, there's neither a maximum or a minimum. So if it stays negative or stays positive, then same deal, okay? The second derivative test, so this one's new. If a first derivative is 0 and the second derivative is negative, then there's a local maximum, okay? So instead of doing the positive to negative change, we can do the second derivative instead, okay? If the first derivative is 0 and the second derivative is positive, then it's a local minimum. Note, this test doesn't work if the second derivative is 0 or if the second derivative doesn't exist. So obviously if the second derivative isn't there, we can't test anything with it, okay? So we'll talk more about what those mean as we go, but there's the theorems off the top, okay? The first thing that we need to kind of review is concavity. So we talked about concavity a little bit in Math 30 when we were talking about polynomials and changes in concavity, right? So that was the happy face versus sad face. Okay, so concave up kind of looks like a happy face, concave down kind of looks like a sad face, and it can have portions of each, right? So all of this is concave up. So I could draw a nice big like smiley face, right? There's my concave up. Or we can picture it as it could fill water, right? It could hold water in all of that concave upness, okay? At the inflection point, that concavity switches, and now we have this sad face, right? We have concave down. So that is where it's pointing down, right? So pointing up versus pointing down, and then the point in the middle there is that inflection point. So if a graph is concave down, the first derivative is decreasing, okay? This means that the slope of the graph is getting less and less negative or more positive. If a graph is concave up, the first derivative is increasing. That means the slope of the graph is getting less positive or more negative, okay? So if we kind of look back at our picture there, see how here we've got a concave up, where as we are going from left to right, our slope is increasing. So it's going from negatives to positives. As we're doing concave down, it's going from negatives to, from negatives to positives, and then from positives to negatives, right? So that's what this one's saying. the method to test for concavity is to find the second derivative. So just like to figure out if a graph was increasing or decreasing, we checked the first derivative, we can check the concavity using the second derivative. So if the second derivative is negative, the graph is concave down. If the second derivative is positive, the graph is concave up. So we're going to do those little like section, x is less than 2, let's say. What's happening? It's negative. What does that mean? Right? So we're going to do that kind of thing again. At a point where the graph switches concavity is an inflection point, and that would be where y double prime is equal to 0. Okay? So, example. 4, we've got f of x is equal to 2x to the 4 minus 4x squared plus 1. We're going to find the extrema, we're going to find intervals of increase and decrease, and we're going to find the intervals of concavity and inflection points. Okay, so the first thing that we like to do is we like to think, okay, what's our domain? So for this one, x is equal to all real numbers, right? This is just a polynomial. So we're going to do f prime at x, and we're going to test for increase and decrease, okay? So f prime at x, we're just doing the derivative, so the 4 comes down, we have 8x cubed minus 8x, and then obviously that goes away. And the points where it's going to change are the points where this is equal to 0. So we set this thing equal to 0, and that gives us our like boundary points, right? So for this one, I'm going to factor out an 8x. So then I have x squared minus 1. That x squared minus 1 is going to factor into an x plus 1 and an x minus 1. And then from this, we can say, well, x is equal to 0, x is equal to negative 1, x is equal to positive 1. So there are our 3 points that things are going to change, okay? The other thing that we want to know about these points is what are our y values doing, right? So if we figure out, okay, these are the special values of x, if we want to know the y coordinate on that original graph, remember that we're plugging back into that original function. So if I plug a 0 in, I'm going to get a 1. If I plug a negative 1 in, I'm going to get y equals negative 1. If I plug a positive 1 in, I'm going to get y is equal to negative 1. So there's the points on our original graph where those would be, okay? So if we look at, okay, here's my, if I make myself a little chart, if I want to look at increasing and decreasing, I'm going to go x is less than negative 1. I'm going to go x is between negative 1 and 0. I'm going to go x is between 0 and 1. And then I'm going to go x is greater than 1. And then we want to figure out what f prime at x is for all of those. And remember that we don't need an actual value. We just need, is it positive or is it negative? So we're picking any value that is less than negative 1. So we could say, okay, put a negative 2 in, and this time we are just going into f prime, right? We want to know what this f prime function is doing. So if we plug in a negative 2, we end up with a negative. If we plug in something between negative 1 and 0, let's say negative 0.5 is probably the easiest, we end up with a positive. If we go between 0 and 1, again, probably 0.5 is the easiest, then we end up with a negative. And then if we go greater than 1, so we'll actually plug this one in. So if I say, okay, I'm going to pick a 2. So 2 cubed is 8, right? So then this is 8 times 8, which is 64, minus 8 times 2, which is 16. That's obviously still a positive number, right? So then we know that this is decreasing, increasing, decreasing, increasing. It's weird for me to not say, does that make sense? But you can't reply because this is a video, and so learning curve for all of us. Here we go. For f prime, I guess on that note, if you guys do have questions, pause them, jot it down, and when we do Google Hangouts every couple days, you can ask those questions, or obviously if it's more pressing, you can always send me an email. So there were our intervals of increase and decrease. Now we're looking for our intervals of concavity and the inflection points. So we're going to do our second derivative, because to test for concavity, we want to look at whether our second derivative is positive or negative. So we're doing the derivative of this guy. So the 3 is going to come down, turn that into 24x squared minus 8. And again, the point where that concavity is going to switch is going to be where this is equal to 0. So those are our inflection points. And then on either side of that inflection point, we're going to have different, is it positive or is it negative, concave up, concave down, okay? So we set that equal to 0. We're going to figure out what this looks like. So I'm going to factor out an 8. So then it's going to be 3x squared minus 1 is equal to 0. So then obviously if I divide both sides by 8, still 0. I'm going to move the 1 over, so 3x squared is equal to positive 1. Divide that by 3. So then x is equal to plus or minus root 1, which is just 1 over root 3. Okay? And then again, to figure out the y value, and we're going to use that to sketch the graph later, to figure out the y value, we're plugging into this original function. So y is going to be equal in both of those cases to negative 1 over 9, because it's to the 4 and squared. So even though one's positive, one's negative, they both end up positive when we plug them back in here. So these are our boundary points. So we want to look at where x is less than negative 1 over root 3, then where x is between negative 1 over root 3 and positive 1 over root 3, and then where x is greater than positive 1 over root 3. So same sort of deal. Now we're looking at, this should be an x. Now we're looking at what is that second derivative doing? Is it positive or negative? So I just want to pick any value that's less than negative 1 over root 3. So I just typed that number into my calculator, figure out what it was as a decimal, and then went to the nearest whole number, otherwise plugged that in. So when I did that, I got a positive. This one, easy to pick a number, right? So definitely 0 is between those two things. If I plug a 0 in here, I get a negative 8, so that's a negative. And then again here, I just figured out what this was as a decimal, picked the next biggest whole number, plugged that in, and I got a positive value. Okay, so what those means is positive means concave up, negative means concave down, and then positive means concave up. Okay, so the next thing that we're going to do is sketch this graph. And it's going to look something like this. So right away from the beginning, we know that we've got a y-intercept at 1. So we can kind of sketch that in right away. So here's 1. There's a point that we know. We know that at negative 1 and positive 1, we've got maxes and mins, right? At negative 1, it goes from negative to positive, so that has to be a minimum, right? And we already figured out that at x equals negative 1, y is equal to negative 1. So here is a point, and then at 0, it goes from positive to negative, so that's a max. And then at 1, it goes from negative to positive, so that's a minimum again. Okay, so, and again, I'm using these points that we found before, okay, as kind of my plot points. And then we know in between these, so negative 1 over root 3, which is about here-ish, kind of like 2/3 of the way from 0 to negative 1, it's going to have that inflection point. So that's where it's going from being concave up to concave down. And then same deal, this graph is symmetrical, which is kind of nice. So we have something that looks like that. Okay, so see how this part is kind of like a ladle, it's concave up. Water could no longer sit in there past that point. It's starting to kind of slide off there. So there is the rough sketch of our graph. Pretty accurate. We could graph this in our calculators and see that we are pretty close. Okay, one more example like this. So for the function f of x equals x times root 9 minus x all squared, all square rooted. We're going to find those local extreme values and intervals of increase and decrease using that first derivative test. Then we're going to use a second derivative test to find any points of inflection and intervals of concavity, and then we're going to sketch the graph. So this is going to take the whole page. So the first thing that we're going to do is domain. So we know that because we have a 9 minus x squared under a square root, that 9 minus x squared has to be greater than or equal to 0, right? Because we can't square root anything that is less than 0. So then we know that 9 has to be greater than x, or greater than or equal to x squared. So from that, we can figure out that 3 has to be greater than, or equal to, that eraser didn't work very well. Let's fix it. 3 has to be greater than or equal to x, and then negative 3 has to be greater than or equal to x, okay? So if we take those two together, write it in a more conventional way, that means that x has to be between negative and positive 3. Because anything outside of those values would make that, what's under that radical symbol, negative, and we can't square root that. So there's our domain, okay? And then obviously we're only testing values within that, because if the thing doesn't exist, it can't have a derivative or a second derivative. So the first thing we're going to do is do the first derivative. So we've got f prime at x, and I would make sure that you're kind of splitting this page, kind of going into the margin a little bit. We're tight on space on this one. So we're going to do the derivative of this guy. Because there's two separate things going on here, we need to use the product rule, okay? So we're going to do the first, right? So x times the derivative of the second. So the derivative of this big guy, right? Remember that this is the same as 9 minus x squared, all to the 1/2. Can you guys see that? Hopefully. So I just want to make sure you guys can see what I'm seeing that you're seeing. Does that make sense? Who even knows? Well, hopefully. So we're going to bring that 1/2 down, and then we're going to leave the 9 minus x squared inside, and then 1/2 minus 1 is negative 1/2. Then we need to multiply by the derivative of the inside. So the derivative of 9 is 0, derivative of negative x squared is negative 2x. Okay, so there's the first times the derivative of the second plus the second times the derivative of the first. That one's much nicer. Okay, so we're going to simplify this up a little bit, and then we're going to set this thing equal to 0. So we've got a 2 and a 2, those are going to cancel. So we've kind of got x times x, we've got a negative, so negative x squared on top, and then this whole thing is going to drop to the bottom. I'm going to write it as a square root again. So we've got negative x over the root of 9 minus x squared, and then here we just have plus the root of 9 minus x squared. And again, we're going to set that thing equal to 0 to figure out what those critical points are. So if we multiply everything by a root 9 minus x squared, then this times itself, or sorry, if we multiply each denominator by that, or multiply each numerator by that, then it would cancel here. This times itself would just become what's inside, so 9 minus x squared without the square root. 0 times that stays a 0, and then as I said, if we multiply the top by this, then the top and bottom cancel out. Okay, so that makes it a lot easier for us to see what's happening here. Then we can kind of collect like terms. We've got negative 2x squared plus 9 is equal to 0. If we move the 9 over, divide both sides by 2, or negative 2, we're going to end up with 9 over 2. Okay, so then x is going to be equal to plus or minus 3 over root 2. because square root of 9 is 3, and then square root 2 is root 2. Okay, so if we plug either of those two values in to our original function up here, then we would get a y value, respectively, of plus or minus 4.5. So again, that's just to give us some plot points for when we sketch the graph later. So that's just plugging those things in, okay? The other thing that could be a critical point here is if the root, so all of this is for when the top is equal to 0. Remember that if this just independently is equal to 0, this thing isn't, f prime at 0 is going to also be a critical point, and it's going to not exist. So those are the endpoints here, okay? So we've got root of 9 minus x squared equals 0. I'm trying to figure out what's happening there, okay? If I go if I square both sides, 0 squared is just 0. So then I have negative x squared is equal to negative 9. Divide both sides by a negative. We get x is plus or minus 3, okay? When I plug a 3 into either of these things, either a positive or a negative, I'm going to get y is equal to 0. So those, because if we think about our domain from earlier, those are our endpoints for this graph, okay? And we'll see that once we sketch the picture. Okay, so we've got x, and we've got x is less than negative 3. We know that at that point, f prime of x is not going to exist, right? Because we know that our domain, according to our domain, the graph doesn't exist there, so we can't have a derivative there. Between negative 3 and 0, which is, not 0, between negative 3 and negative 3 over root 2, okay, that's another one of our critical points here. If I plug in values, and we'll get to that in a second, we can figure out whether that's positive, negative, and then whether it's increasing or decreasing based on that. So if it's between negative root 3 over root 2 and positive root 3 over root 2, there's another interval between those critical points. And then this one is not rooted. I don't know why I keep rooting it. And then 3 over root 2 less than or equal to 3. Okay. So, and then obviously we know if x is greater than 3, that derivative is not going to exist. So if we pick a value that's in between these two, okay, so again, if you don't know what this number is, you can just crunch it as a decimal, figure out the nearest whole number that's easy to use, plug that in, you should get a negative, okay? In between these two, a 0, I plug that into the original function. That's going to be 0 times blah, 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 blah. It's going to be a 0. Is that positive or negative? We don't know. So let's pick something other than a 0. Okay. When I do that, I get this as a positive. And then same deal here, pick a number between these two numbers, plug it in, I get a negative. So we know that this will be decreasing, increasing, decreasing. So between these two spots, we're going to have a minimum. Between these two spots, we're going to have a maximum. I'll leave that there for a second, sorry. So teaching on a DocuCam without anybody telling me what to rearrange where the camera is pointing is also a learning curve. So many learning curves. You guys can also always pause it if I go too fast or whatever. It's nice. This is your own custom classroom. So there's our intervals of increase and decrease. Now we're going to do our intervals of concavity. So now we're looking for f double prime. The first thing that I'm going to do is rewrite f prime in a way that's easier to differentiate again. Okay, so I'm going to write f prime at x again. And I'm going to write it as 9 minus x squared all to the 1/2 times 9 minus x squared minus x squared. So I've taken what I had there, I've flipped the order first, and then I've factored out a 9 minus x squared to the 1/2, okay? So when I do it out of this term, I have 1 left over, because to the 1/2, taking that out, wait, no, did I flip it? I can't remember. Yeah, I did flip it. Okay, so when I take this one, I factor it out to the, oh sorry, it's a negative 1/2, that's why. I was like, why is this happening? So when I factor out a negative 1/2, positive 1/2 minus a negative 1/2 turns into a 1, right? So we're just factoring this guy out. So that's gonna make it a little bit easier to differentiate. So then this one, again, is 9 minus x squared all to the negative 1/2, and then we can combine this guy to 9 minus 2x squared. So this is going to be easier to differentiate than that was, right? So now we've just got a product rule again. So f double prime at x is equal to, we're going to take this guy, so we're going to do the first one, so 9 minus x squared to the negative 1/2 times the derivative of the second one. So the derivative of this guy is negative 4x plus, and I'm going to do it on a separate line because I know I'm going to run out of room. The second one, so 9 minus 2x squared times the derivative of the first one. That negative 1/2 is going to come down. 9 minus x squared is going to stay in the middle. Then negative 1/2 minus 1 turns into negative 3/2, and then we still need to multiply by the derivative of the inside, so negative 2x. Okay, so when we simplify, we collect all of that, we're going to get negative 4x times 9 minus x squared plus x times 9 minus x squared to the negative 3/2 times 9 minus x, or sorry, 9 minus 2x squared. So it's this part. Okay, so there is our second derivative. If we set this thing equal to 0, okay, that's going to tell us where our point of inflection is. So to solve this, we need to think through, okay, if I divide both sides by common factors, we end up with super complicated stuff. So if we just look at this and think logically about it, if this is a 0 and this is a 0, then we have 0 plus 0, right? Because if the x is a 0 and an x is a 0, that turns this whole term into a 0 and this whole term into a 0. So we know that this is going to be equal to 0 when x is equal to 0 without actually having to do that complex math. Okay, so then we know that our point of inflection, which sometimes we call a POI instead of POD like we did in Math 30, is at 0, and then if we plug in x equals 0 back into here, we're going to get the y coordinate is also 0. Okay, so then we can figure out which side's concave up, which side's concave down. So we're going to go x is less than 0, x is greater than 0. So if I plug in negative 1, say, to this one, then I get a positive value. So there's my concave up. If I plug in a, say, positive 1, then I'm going to get a negative value, and then this is concave down. Okay, so my graph is going to look something like this. So we know right away that at negative 3 and positive 3, the y values at both of those spots are 0. That's right over here. And that's the edge of our domain, so the graph is going to end there. We also know that our inflection point is at 0, 0, so we're going to plot that. Okay. We know that at x equals positive or negative 3 over root 2, so we're going to just say that that's about half. Okay. It's slightly different than half, but close enough. That's our max and min points. So at our positive root 3 over 2, that's when we would have gotten our positive 4.5. And it's not root 3 over 2. I'm so used to that from Math 30. It's 3 over root 2. Okay, so there's our positive 4.5 there. And then here's our negative 4.5. That's our minimum. Okay, so our graph looks something like that. See how we've got concave up, we've got a smiley, concave down, we've got a sad face, right? So I just draw those little eyes sometimes to like put them in, but you don't have to. They don't need to stay. It's just a little memory trick for us, okay? So there's the first half of section 5.3. We're gonna leave it there for right now, and we will pick it back up in 5.3 section 2. Again, if you guys have any questions, just definitely let me know. Pause it, write them down, either save them for when we do a Google Hangout, or send me an email, okay? And if anything didn't make sense, you can always rewind. So helpful. Okay, arrivederci.